Swayam Prabha. Digital India. Educated India.
Hello students, welcome to this lecture. In the last lecture, we started discussing about molecular spectroscopy. In particular, we looked at the electromagnetic radiation, why we call electromagnetic radiation its name, and what are its properties, and how it interacts with matter. Today, in this lecture, we would continue our discussion from there. But before we go and look at some spectroscopic methods or some spectroscopic techniques, we will first discuss about little more about this electromagnetic radiation, and in particular we will talk about the electromagnetic spectrum. We know that electromagnetic radiation comes in different ranges of energy. The light that we can see we call that visible light, but then we also know that and this light is part of this electromagnetic radiation, but then there are other waves, other radiations which we cannot perceive through our eyes, and this radiation, the entire spectrum of this radiation is shown here. It is a common practice to arrange these electromagnetic radiations in their increasing order of energy or increasing order of wavelength. As we know that for a given electromagnetic radiation, if its energy is given by E, it is associated with a frequency given by h nu, where h is the Planck's constant. We can alternatively express this electromagnetic radiation, instead of expressing it in terms of frequency, we can also express it in terms of its wavelength. Then the relation is hc by lambda, or we can use it in terms of its wave number nu bar, which is given in the unit of meter inverse or centimeter inverse, or alternatively we can also describe it in terms of its period, because electromagnetic radiation is a wave. So, therefore, different characteristic properties of the wave can be used to express the energy of the particular electromagnetic radiation. Now, in this picture you can see in one range we have the radio waves or TV waves, and the other range is gamma rays. In the left hand side of this picture, you see the radiation with very low energy. So, from left to right of the spectrum, the energy increases, and since energy is inversely proportional to the wavelength, so therefore, from left to the right the wavelength decreases. Now, radio wave and TV waves have highest wavelengths. Of course, that is why we use them for radio transmission or television transmission, because we require waves which can travel faster because of their large wavelengths, but these waves are associated with very small amount of energy. Larger the wavelength, less is the energy associated. So, using this radiation, low energy radiation, we can of course do transition from one stationary to another stationary state, but in that case our stationary states should be very closely spaced, or the energy difference between these stationary states must be very small, such that these low energy radiations like radio waves or TV waves can do this kind of transitions. So, what kind of levels satisfy that criteria? Of course, the spin states either through the nuclear spin or through the electron spin. The spectroscopic techniques that probe these states are NMR or ESR, and in this NMR or ESR you use this low energy radiation, and we normally use a range of units to express different electromagnetic radiation. We follow certain convention, but the idea behind using a particular unit for a particular radiation, particular part of this electromagnetic spectrum, is that sometimes what happens is that the particular unit, if we use and the associated numbers become so difficult to communicate. For example, if we are choosing to express a particular radiation in a certain unit whose number becomes 0.00031. So, that becomes very difficult to communicate with each other, there are 0 point so many zeros and 31. Instead, if we can convert it to a unit, a different unit where the number would simply become 31. So, it will be very effective to communicate, effective to remember. So, therefore, for that purpose we are going to use different unit system for different part of this electromagnetic radiation. In the beginning it may appear confusing to you, but once you get used to them you would start realizing that this is perhaps is very convenient to communicate with each other if we follow different units to express different part of the electromagnetic radiation. We will also in our course of discussion will have some pointer at that direction. Now, as we go little higher in energy, we see the range of energies which can induce the rotational change in the molecule. So, this range of electromagnetic radiation can cause a molecule to rotate faster. So, this energy range I usually go from microwave to millimeter wave. So, since they can cause molecular rotation, so we do when we look at rotational spectroscopy, we use microwave radiation or millimeter wave radiation, and the units that we normally use to express this radiation goes in gigahertz unit. You see that we have in the scale of gigahertz it goes from 1 to 1200. So, these numbers are very easy to communicate. So, that is why we use gigahertz unit for rotational spectroscopy. Alternatively, we also use centimeter inverse unit. So, you can see that it goes from 0.03 to let us say 40 or 400. So, alternate either we express in terms of gigahertz or in centimeter inverse to describe rotational spectroscopy. Now, as we go further higher in energy, we see that the next range of energies or next range of radiations can induce vibrational changes in a molecule. So, to vibrate a molecule, to vibrate a particular bond in a molecule, it requires more energy than what it takes to rotate that molecule. To do this vibrational excitation or vibrational changes, we normally use infrared radiation. So, it goes from far infrared to mid infrared and near infrared, and to express these radiations we again use centimeter inverse unit. Normally a vibrational frequency is like a bending frequency or a stretching frequency is given as a few thousand or 1200, 1700 wave number. So, this centimeter inverse unit is the most commonly used unit for expressing infrared radiation, and infrared radiation is used to do vibrational spectroscopy because this radiation has just about enough energy to cause the vibrational state to go from one vibrational state to another vibrational state. Further, when we go higher in energy, we see we can do electronic excitation. So, that means since electrons in a molecule are subjected to the nuclear the electrostatic field of the nuclei. So, therefore, it takes even more energy to actually do electronic transition, and to carry out this electronic transition we normally use visible to visible and ultraviolet region, and sometimes also near infrared region for very low close lying electronic states. So, to express this electronic range we use nanometer or the wavelength. So, visible light, visible radiation or the ultraviolet radiation will have a few hundred nanometer of wavelength. So, this is used for UV visible spectroscopy. We also, so this is for excitation of from one electronic state to another electronic state, we can use UV or visible radiation. That is why we also call them as UV visible spectroscopy. But if I want to completely remove one electron from the field of nucleus, I need to provide even more energy. In that case, we normally go ultraviolet to far ultraviolet region. So, in this case, these experiments are called photoelectron experiments, where the electron is completely going out of the nuclear environment. In case of electronic transition, normal electronic transition, the electron still remains in the within the influence of the nuclei, but in case of a photoelectron experiment, we are completely removing the electron from the nuclear field. So, that obviously requires more energy, and to express those energies we normally use electron volt. So, you see we use far ultraviolet UV or far UV energy to ionize the valence electrons of a molecule, and if you want to ionize the core electron of the molecule, of course, you have to provide even more energy, and for that you use X-ray radiation, and gamma radiations have even more energy. So, here we see that this electromagnetic spectrum gives us a wide range of possibilities to do spectroscopy depending on what we want to achieve, whether we want to only rotate the molecule or whether we want to vibrate the molecule, or whether we want to change the electronic arrangement of the molecule, will take a different source of radiation. But the other properties of the electromagnetic radiation apply to all the radiations that we have discussed. It is only their energies are different. So, using different parts of this electromagnetic spectrum, we will discuss more about spectroscopy. So, what we would do, the plan of this course is that we would first go to the rotational spectroscopy. So, therefore, we will talk about the low energy range, then we will go to vibrational spectroscopy, and finally, we will enter to the range of realm of electronic spectroscopy. So, the first point of our discussion would be the rotational spectroscopy. As I said, when we do rotational spectroscopy, of course, we are concerned about how the molecule would rotate and how the rotation of the molecule would cause some change in the molecule such that the molecule can now communicate with the electromagnetic radiation. In other words, it can absorb radiation or it can emit radiation. So, now we will be interested in learning about how we can define the rotational motion of the molecule. When I say a molecule, of course, I can mean a simple diatomic molecule or a linear triatomic molecule or a tetrahedral molecule or a trigonal bipyramidal or a molecule which is very large and having no particular symmetry. So, I must be able to provide a unique definition no matter what kind of molecular system I am talking about. So, therefore, to achieve that, we have to do some classification of the molecules for the purposes of rotational spectroscopy, and we do this in the following way. When we have imagine you have a very extended molecule and you are trying to picture that this molecule is rotating. You can picture this rotation in many different ways. So, your visualization is going to be very different from mine. So, therefore, it is better that if we can agree to a particular convention. The convention that we have decided to use for these purposes is that no matter what is the shape of the molecule or what is the size of the molecule, you always have a center of gravity. So, first find out the center of gravity of this molecule. Suppose you have a molecule with a very random shape, and I determine the center of gravity of this molecule. At this center of gravity, imagine 3 perpendicular axes. Call these 3 perpendicular axes, give them some name A, B, C. These 3 axes are called principal axes of this molecule. The origin of this axial system is the center of gravity of this molecule, and these are 3 mutually perpendicular directions A, B and C. Now, we have to imagine that the molecule is rotating along these principal axis, along these 3 principal axes. Now, when a molecule rotates along a particular axis, it has a corresponding moment of inertia. So, corresponding moment of inertia is given as I equals mi r(I) square, where mi is the mass of a particle in this molecule which is rotating around a particular axis, and r(I) is the distance of this particle from that particular axis. So, if I am talking about the moment of inertia along A axis, then I would find out the distance of this particle from the A axis. When I talk about the moment of inertia around B axis, I will find out the distance of this particular particle from the B axis. So, therefore, this distance r I is from the distance of the from the axis, and if this particle which in our case is a nucleus, if this nucleus happens to be on the axis, then of course r becomes 0. So, therefore, for that particular particle will not contribute anything to the moments of inertia. So, therefore, these 3 axes A, B, C are called principal axis, and corresponding to each of these axes A and B, A, B and C, I can define I A, I B, I C as the 3 principal moments of inertia, where I A is given as the moment of inertia around A axis, I B is around B axis, and I C is around C axis. Now, there is one more convention. We normally provide this name C or the index C to that principal axis which has the largest maximum value of moment of inertia. So, this we follow this tradition, the convention that I C is that principal axis around which the moment of inertia is the maximum, I B is the second maximum direction, and I A is that axis around which the moment of inertia is the minimum of the 3. Okay. So, keeping this in mind, we will try to now classify different molecules. First example that we would take is that let us consider a linear molecule. When I have a linear molecule, let us say I have a linear triatomic molecule. Of course, I can do this analysis, extend this analysis to either diatomic or even polyatomic linear molecules. So, when I have a linear molecule, in this case I am taking the example of HCN. So, of course, I would first step is that find out the center of mass or the center of gravity here. So, this is of course, since nitrogen is heavier. So, the center of gravity is going to be closer to nitrogen atom here. So, as you can see here, since all 3 atoms in this are on the same axis. So, therefore, center of gravity is also on the axis. So, this is center of gravity, and around that I drew 3 mutually orthogonal axes A, B, C. Now, you see I have called this axis as A axis. Why is it so? Because I see around this axis A, if I try to calculate the moment of inertia, I would see that okay, where is nitrogen atom? What is the distance of nitrogen atom from this axis? It is on the axis. So, therefore, the distance is 0. So, nitrogen does not contribute anything to a moment of inertia. Similarly, carbon and hydrogen are also present on the axis. So, therefore, R I, which is the distance of this nucleus from the principal axis, is 0. So, therefore, I A in this case is 0. What about I B and I C? I B is perpendicular to the plane of the screen. So, if I try to rotate this molecule around this B axis, you would see that HCN molecule will rotate on the plane of this screen. So, this is called an end over end rotation. Alternatively, if I rotate around C axis, which is shown as the plane of the screen, if I rotate the molecule around C axis, you would see that the molecule will rotate perpendicular to the plane of the screen. Around B axis, it will rotate on the screen, and around C axis it will rotate perpendicular to the plane of the screen. But in both cases, you would see that the moment of inertia around IC and around C axis and B axis will be same. So, in this case IC becomes equal to IB and IA equals 0. So, when this kind of criteria is satisfied, we call this type of molecule, we classify them as linear molecules or linear rotors. And then we go to another class of molecules, where we would see now we would require that two of the principal moments of inertia are equal, 2 of i's are equal, and the third is not 0. So, here in this case linear case, two of them are equal, that is all right, but the third became 0. But now we are telling the third should not become 0, and in this case we can we can imagine two cases. One case would be where suppose I c is equal to I b and this is greater than I a, or the other way is that I c, the largest principal moment of inertia I c is greater than I b, which is equal to I a. So, based on these two criteria we are going to classify the molecules further. So, whether condition 1 is satisfied or condition 2 is satisfied, we call these systems are symmetric top. And now we will look at one example and see where it belongs to. The example here is methyl iodide CS3I. So, you can see iodine atom is present here. Now, if you try to find out the center of gravity, of course, you would see that the center of gravity will be very close to iodine, because iodine is much heavier compared to the carbon or hydrogen that we have. So, once we have the center of gravity, we draw three perpendicular axes. One is A, which is along the C I axis, the other two are B and C, one is on the plane, another is perpendicular to the plane. Now, you see, if you we call this symmetric top, because if you try to imagine that you are rotating this molecule along this A axis or around C I bond, you would imagine that it is as if a top is rotating. So, that is why you call it a symmetric top. But let us try to find out what could be the values of I A, I B and I C. First of all, what about I A? You see, when I consider I A, two of these atoms, iodine and carbon, are on the axis. So, therefore, they will not contribute anything to the moment of inertia. So, therefore, when I am calculating I A, in that case iodine will not contribute, and since the moment of inertia depends on the mass and iodine has very large mass. So, therefore, this moment of inertia is going to be very small, because iodine, the heaviest of all, is not contributing. Now, when you look at B or C axis, so that when you are doing this end over end rotation around B or C axis, you will see that all 5 atoms, the CS3 portion as well as iodine, all are changing their position. So, therefore, there is a finite distance from the B axis and C axis. So, they will all contribute to the moments of inertia. So, therefore, I B and I C are going to be equal, and they are going to be greater than I A, and since I A is not 0, unlike a linear molecule. So, in this case you would see I B and I C are equal and I A is much smaller. So, therefore, this methyl iodide belongs to this class of symmetric top. There is a separate name for this class of symmetric top, we call them prolates. So, here where this condition is satisfied. Now, let us take another example. This example is benzene. In case of benzene, you know that it is a planar molecule. So, the center of gravity is at the center of the ring. Now, I am drawing 3 axes. You can see A axis, B axis on the plane of the screen, and the C axis is perpendicular to the plane. Let us see why it is so. When we consider A and B axis and try to rotate the molecule around A axis or B axis, we would see that around B axis, these carbons and these hydrogens would not contribute, because they are on the axis. In case around A axis, you would see that even if we do not see any particular atom present on the particular axis, but when you do the distance calculation, you would see that this around B, the principal moment around B and principal moment around A would be same, because you can imagine that these hydrogens are farther from B axis compared to the A axis. So, therefore, there will be some cancellation, and you would see that the principal moment of inertia around A axis and B axis will be equal. Now, what about the principal moment along C axis? When you do the rotation around C axis, which is the plane of the perpendicular to the plane of the screen, you would see all the atoms present in this molecule would rotate. So, would contribute to the principal will contribute to the moment of inertia. So, therefore, that moment of inertia is going to be greater. So, that is why we call this as C axis. IC is greater than IB and IA, and IB and IA are equal. In this case, we call these rotors as oblate. Normally, many planar molecules satisfy this relation. Now, we can have another example where this is a tetrahedral molecule and this is an octahedral molecule, is methane and SF6. You would see that we can find the center of gravity, which would be on the central atoms in both cases, and then we calculate the three principal moments of inertia. You would see in this case IA will be equal to IB will be equal to IC, and such systems are called spherical tops. And finally, so the spherical top requires all three moments of inertia to be the same, and finally, we have the so called asymmetric top, where there is no relation between IA and IB and IC. They can simply have any random value. Of course, we know that we will call that axis principal axis C, which has maximum value of moments of inertia, but majority of the molecules that we know, they come under asymmetric top. But there are some molecules with specific symmetry. For example, the linear molecules would come to linear rotors. The molecules like methyl iodide or methyl chloride, they would come under prolate. Molecules like benzene or BCl3, they would come under oblate symmetry. Tetrahedral, octahedral molecules, they come under spherical top symmetry, and majority of the molecules come under asymmetric top. In the next class, we will take a few of these classes of molecules and see how the rotational or microwave spectroscopy of these different classes of molecules differ from one another. So, that would be the topic of our discussion in our next class. Thank you for your attention.